Так, добрый день, давайте начинать лекцию. Uh, so we continue studying list decoding. In the last class, we discussed Johnson bound, which relates the minimum distance of the code and the properties of its list decodability. There is another theorem of this type, and I will start with its statement. So the theorem is the following. Every NKG code. So here it's important, there are only two important parameters, the block length and the minimum distance. Q and K are not important at all and won't be used in the conclusion. Code is E n plus 1. So the size of the list is n plus 1, list decodable. And E here is at most some cumbersome value. So whenever the number of errors is less than n minus the square root of n times n minus d. So this upper bound is hard to memorize, and also it looks completely counterintuitive. So I will explain its meaning. What means that we have a NKG code? That means that the minimum Hamming distance between any two words is at least d. To understand this theorem, it's better to switch not from the number of positions where two code words coincide, but to the number of are different, but to the number it's worth to switch to the number of positions where they coincide. Let's denote it, say, by C. So C of xy is n minus d of xi, and this is the number of positions where they coincide. I's such that xi coincides with yi. And so if we switch to the number 2c, then d becomes, instead of d, we will have some value, let's denote it by u, which is equal to n minus d. And this is the number, the maximal number of positions, where two different code words may coincide. Of coinciding symbols in different code words. So also for Hamming ball, instead of speaking of Hamming ball, say of radius E, we can speak of Hamming balls, so to say, of co-radius U. This is the set of all strings which coincide with the center of the ball in So we can say that the Hamming ball of radius E is a set of all strings that coincide with Z in at least n minus E positions. Also, we can switch to the number of coinciding positions when we speak of the ball, about the ball. And if we make this switch, then this bound, this this will become n times u. You see, n minus d is equal to u just by definition, and n minus this is just the co-radius of the ball. So the reformulation of the theorem is the following. Assume that C of xy is at most u for all different code words. Then for every z, there are at most actually strictly less than square root of n u code words coinciding with z in more than, oh, sorry, there are strictly less than n plus 1 here. There are at most n plus 1. N plus 1 code coinciding with z in strictly larger than square root of nu positions. So in this form, the theorem is easy to memorize and understand. And also it's worth to compare it with what we know. So we know that actually if we consider E, the number of errors, equal to about d over 2, so we know that actually such code corrects that such a code corrects about d over 2. And in terms of u, that means n minus u over 2 errors. And that means that every Hamming ball, this implies that for every z, there is at most one code word coinciding with it in at most n minus that much. In at most that in at least n minus d over 2, which is n minus u over 2, which is n minus u over 2. So in terms of U, of the number of coincidence, we know that such a code has the property that for every Z, there is at most one code word coinciding with it in n plus U over 2 positions. And now you see what do we do. Here n plus U over 2 is the arithmetic mean of n and U. Now, instead of arithmetic mean, we consider geometric mean. It's well known that geometric mean is less than or equal to the arithmetic mean. And so we lower this bound. So now we consider less positions where we require the coincidence. That means that we enlarge the size of the ball, and we pay for that. Previously we had at most one code word. Now we claim that there are at most n plus 1. So still n plus 1 is not much, but we treat in this theorem the radius of the ball for the number of code words. We increase the radius by changing the arithmetic mean by a smaller amount, which is geometric mean, and we increase the number of code words. So this is the meaning of this theorem, which makes it easier to memorize and understand. Так, есть ли вопросы по формулировке теоремы? Все ли тут понятно? Что-то я не слышу, чтобы хоть кто-нибудь что-нибудь говорил.
Да, понятно.
Ага. Okay, so we will use this reformulation in the proof. So we will assume that different code words coincide in most U positions, and we will consider any Z and consider all code words which coincide with that in larger than that much positions, and we will prove that there are at most n plus 1 of them. In the proof, we will again use the geometric fact used in the Plotkin bound. So we will transform those code words in some real valued vectors so that those real valued vectors form obtuse pairwise angles. And we know that and they will live in n-dimensional Euclidean space. And we know that in n-dimensional Euclidean space, there are at most n plus 1 such vectors. So how to compute such vectors? So once again, so we have some Z, and we have a code words x1, x2, xn, and we know that the number of coincidences between xi and z is larger, strictly larger than square root of nu. And from that, we need to derive that n is at most n, capital N is at most little n plus 1. So this is our goal. And to this end, for each xi, consider the following indicator of positions where they coincide. Call it xi. So actually xi will be a random value, which is obtained as follows, with the following distribution. We choose a random position in Z, and the random value is 1 if the random variable is 1 if in that position Z and Xi have the same symbol and 0 otherwise. So Xi is a random variable with values in 0, 1, defined as follows. Xi if equals to 1 if Xi, J's position of Xi is the same as J's position of Z, and 0 otherwise, where J is chosen among all possible positions at random with uniform distribution. Or in other words, we can consider Xi just as a sequence of bits, which is actually we will use both viewpoints on Xi. We will consider Xi as a random variable, and also we will consider Xi just as vector. So Xi consisting of Xi of 1, Xi of 2, a vector of 0, 1, so length n. Now we will transform each, using this viewpoint, we will translate each Xi to a new vector, call it yi, which is obtained as follows. We just take the arithmetical mean of these values. In other words, we take the expected value of Xi and subtract that arithmetic mean from all values. We will obtain a real valued vector. So yi is obtained when we subtract from Xi the arithmetic mean of Xi. And those vectors, we will prove the following lemma, that those vectors form pairwise obtuse angles. And these vectors, this inner product, if we normalize it, dividing by n, has the clear meaning in, it has a name in the probability theory. It's called the covariation of two random variables. So it's covariation of Xi and Xj, or after normalization is just the arithmetic mean of Xi, the expectation of Xi minus expectation of Xi times Xj minus the expectation of Xj. So in other words, we need to show, and once we show the lemma, we are done, because so we have capital N vectors yi, they form pairwise obtuse angle because the inner product is strictly negative, and we know that the maximal possible such a number of such vectors is at most the dimension +1, n +1. So let's see why this is true. So when we take the inner product of such vectors, so what we obtain? So this is, first of all, this is, let's express it, xi minus expectation. When we subtract expectation of xi, we subtract it, of course, from all the coordinates of xi using this representation. So if you multiply these two vectors, then we obtain the inner product xi of xj minus the inner product of xi by all constant vector xj minus the inner product of the all constant vector cj, expectation of cj, xi, xj, and plus now. What do we know about this? So we need to upper bound this sum. Xi and Xj may be upper bound using the fact that any two vectors, that the minimum distance of the code is large, or in other words, any two different code words coincide in at most u positions. So the inner product of xi xj is the number of positions. So let's write it. Xi xj is the number of positions where xi and xj coincide. But if is the number of positions where they are both 1 divided by n, if we normalize the inner product. So how many positions if, is the number of positions where they are both 1. But if they are both 1, that means that they both coincide with z, and so they coincide with each other. And we know that there are at most u such positions. So this is because at most then u over n. Now, this is at most u over n. Now, what can we say about this? But actually, it's worth to rewrite this, because this is all constant vector, and the inner product of this is the same as this. So this can be cancelled with this, and And this may be rewritten just as times the product of expectations. And so for the product of expectations, we can estimate it using the property that the distance is small. So E of xi is just the number of ones in xi, and the number of ones by assumption is strictly larger than nu. So we know that E of xi is strictly larger than nu over n. So the fraction of positions where xi is 1 is strictly larger than square root of u over n. So now when we multiply this square root over n by another square root over n, we will obtain strictly less than minus the square of two square roots, which is equal to u over n. So we obtain u over n minus u over n, which is 0. And so you see that the inner product of any two different vectors, or in other words, the covariation of any different random variables xi and kj is strictly negative. And we have indeed strict inequality because this inequality is strict, which follows from the fact that this inequality is strict. So we have proven our lemma and proved the theorem. Так, понятно доказательство?
Да.
Да.
Хорошо. Okay. Now we have the second theorem, which relates the least decodability properties with the minimum distance. And this theorem is ineffective in the sense that we just have upper bounded the number of coordinates in a Hamming ball, but we have no effective procedure to find the list of such coordinates except the brute force search. And we are interested for which codes we can make the theorem effective. And it turns out that this can be done for Ritz-Salomon codes, maybe for some others, but I know only theorem about Ritz-Salomon. So assume that we have considered Ritz-Salomon codes. Say a Ritz-Salomon code corresponding to polynomials of degree k. That means that the dimension is k plus 1 and the minimum distance is n minus k. And assume that and I need to recall that the alphabet must be larger than the block length. So for Ritz-Salomon code, we can prove the following theorem. I will state the theorem first of all without exact parameters. there is an effective algorithm, polynomial time. That for finds. So as input, that algorithm receives the corrupted table of that polynomial in endpoints, in the chosen endpoints. And it outputs the list of possible polynomials which might produce such a table. And the size of the list will be about n square root of n, which is a little bit larger than by the previous theorem. And the list will contain all the polynomials which coincide with the corrupted table in about square root of n key points, as in the previous theorem. So you see that a Hamming distance is n minus k, which means that the number of coincidences is k. So our algorithm receives any function, call it f. So assume that our Reed-Solomon code is defined as the values, the code words are values polynomial in n certain endpoints. So our the input is the function which maps these values into fq. As input, and outputs a list of n square root of n polynomials of degree at most k, such that the number of coincidences between f and such that that list, such a list that includes all polynomials p of degree at most k, such that the number of coincidences between p and that function is at least about square root of nk. So this is imprecise and will be made precise later. So here we need actually, we will use actually a value which is a little bit larger than this one. What we will see which one. So actually we know that there are even less than n plus 1 polynomials with that property. But effectively, we can compute a list which is larger. So how this can be done? First, we will need to recall some algebra. So if we have a polynomial, say p, one variable polynomial, we say that sum a is a root of p if p of a is 0. But we will need the notion of a root of multiplicity at least, say, m. What does it mean? This means that p of x is divisible by x minus a to the power of m. And this is just the definition. But this can be rewritten as follows. And this other form will be more convenient for us. That means that if we consider the polynomial p of x plus a, that polynomial has no terms, no monomials, of degree less than m. And this is obvious that this is a reformulation of this. Indeed, in one direction, if p of x is equal to x minus a to the m times some polynomial q of x, then this implies that p of x plus a is equal to, so just substitute here x plus a for x, and we will obtain x to the m q of x plus a, seeing that all the monomial have x to the m, so there are no monomial of degrees less than m. And in the other direction, assume that p of x plus I has no such monomials. That means that p of x plus I can be represented in this form. P of x plus a is x to the m times some polynomial, say r of x. And then if we substitute x minus a for x, we see that p of x is x minus a to the m times r of x minus a. So indeed, p of x is divisible by x minus m, a to the m. So we will use this form, the definition in this form. And in this form, it can be easily generalized to multivariate polynomial. We will say that polynomial, actually in the proof we will use two variables. So let's write it for two variables. Some polynomial r of xy has a root, say ab of multiplicity at least n, by definition, if the polynomial rx plus a y plus b has no monomials of degree less than m. In particular, if m is positive, that means that this is indeed a root, because for m1, this means that it has no constant term. And that means that if we substitute zeros for x and y, we will obtain 0. So indeed, a and b, ab is a root, just normal root. Okay, so this will be our definition, working definition of a root, of a multiplicity of a root of the two varied polynomials. Okay. Now, now let's start the proof of the theorem. We assume that we have some function f. And want to find all the polynomials which coincide with f in many points. And those polynomials will be found as factors of another polynomial, and that polynomial will be constructed by solving a system of linear equations. So actually, I should start with the remark that the proof of this theorem is similar, somehow similar, to the proof of the theorem about polynomial time decodability of Reed-Solomon code from errors. In that proof, we're also using a system of homogeneous linear equations, found a polynomial with certain properties, and then we just divided that polynomial by another polynomial, finding the third polynomial. And here we will do something similar. So the first step, we will find a polynomial of two variables. The difference is that now we need a polynomial of two variables. Of small degree. Actually, we will need some strange notion of degree called k degree. The k degree of that polynomial will be small, meaning that less than certain parameter a. We will specify a later, such that that polynomial has roots f xi, f of xi, of large multiplicity, such that for every I, xi, f of xi is a root of R of multiplicity at least certain n. So A and n are parameters to be specified later. And on the second step, we will prove that actually, sorry, I recall, I forgot to say what is k degree. So the definition of k degree. When we compute normal degree, we assume that x and y are counted both as one. So the degree of monomial, say xy, is 2. But now we assume that y is counted k times. So the degree of monomial xi times yj is defined as y plus k times j. So in other words, y is k times more valuable than x. For example, the degree of of x squared y cubed is 2 plus 3k. And the degree of polynomial is the maximum degree of its monomials, as usual. So, and on the second step, we will prove that R of x, P of x, is 0. So if we substitute P of x for y in R, we obtain 0. And hence, we will prove that this means that R is divisible by y minus P of x. And we will derive that we can factor R in irreducible polynomials and just then single out of them all the factors of the form y minus a polynomial of x, all the factors of degree 1 in y, and from all the factors we will extract all the polynomials and among them p. And because of the fact that the degree of R is certainly at most a, even the k degree is less than a, we will know that the list contains at most a polynomials. So this is our plan. And to fulfill that plan, we need to show first the following lemma, stating that the first step can be done with a small a, with a small degree. So in the first step, we will show that if n times n plus 1 times n is at most a squared over k. So if a is large enough, then there is such polynomial. Then there is R of k degree less than a, such that all of those xi, f of xi, are roots of multiplicity at least n. Then there is R, polynomial R, as in 1, call it 1, and call this 2, as in 1. Okay, and actually we need that R is non-zero, of course, non-trivial R. So why is this? So let's understand what means a constraint that R vanishes in a certain point AB. A is taken already, so let's use some other letter. Say CD. So we know that this is one linear equation in the coefficients, a homogeneous linear equation in R's coefficients. Now, we want to write, we argue that actually requiring that this is a root certain CD. C and D are some concrete numbers. That for whatever CD and N we choose, such requirement, such a constraint may be expressed as a system of homogeneous linear equations. And we need to understand how many variables, how many equations that system has. So for example, if we require that this is CD with the root of multiplicity with multiplicity at least 10, what does it mean? That by definition, that means that R of X plus C Y plus D has no monomials of degree strictly less than capital N. And again, this can be expressed as a system of linear homogeneous equations, because if we rewrite this in terms of coefficients, then coefficients with all monomials like xy, x, or y will be expressed as a linear combinations of R's coefficients. Let's see it in example. Let's consider example. Assume, say, that R is, say, x squared plus y plus xy. And assume that we want to write that certain point CD is a root of certain multiplicity. So we just plug here C x plus C and y plus D for x and y. So then we obtain that the following expression: x plus C squared plus y plus D plus x plus C y plus D. So we have x plus 2c x squared plus 2cx plus c squared plus y plus D plus x y plus cy plus xd plus cd. So if we are interested in certain coefficient, for example, coefficient with y, we see that it is obtained as y times 1 plus c. It's a linear combination of coefficients of the initial polynomial. So assume that now this is not just a concrete polynomial, but it has coefficients, say, u, v, w, v. Then this is multiplied, everything here is multiplied by u. Everything here is multiplied by v. And everything here is multiplied by w. And so the coefficient with y is now v plus c times w, I guess, because there is no other y. Yes. So, and this is a linear combination of the coefficient of the initial polynomial R. So this example convinces, I guess, that if we write the constraint that a certain monomial has zero coefficient, then that coefficient is a linear combination, homogeneous linear combination of the coefficients of the initial polynomial and produces one homogeneous linear equations. So, which means that this is a system of how many equations. The number of equations will be equal to the number of monomials of degree n. And we actually know how many of them we have. N times n plus 1 over 2. We have already once calculated that amount. For example, if n is 1, we obtain only 1. We require that the constant term vanishes. If n is 2, we obtain 3. So we require that the constant term vanishes and also x and y. So we have 3 equations. So in general, n times n plus 1 over 2. So now the requirement that all those n, small n, pairs are roots of degree n produces n times n plus 1 over 2 homogeneous linear equations. And such a system has a non-trivial root, non-zero root, if the number of variables is strictly larger than the number of equations. So we need to show that the number of R's so R is the polynomial we are looking for, coefficients is strictly larger than this amount, n times n, capital N times capital N plus 1 over 2. And so how many coefficients it has? So the requirement is that the k degree, recall that the only constraint about R is that the k degree is strictly less than a. So that means that R has all the monomials. R has all monomials x I to the I, y to the j for I plus kj strictly less than a. So, and for each such monomial, R has one coefficient, so one variable. So we obtain one variable in our system. So we need to show the following fact, that the number of solutions of this to this inequality is larger than this amount. So, and actually, this is this follows from our main assumption about. So we assume some relation between our parameters. So you see that our assumption can be rewritten as follows. If we divide everything left-hand side and the right-hand side by 2, then the left-hand side just becomes the number of equations. And the right-hand side becomes a squared over 2k. So we are given that a squared over 2k is larger or equal to the number of equations in our system. So we just need to prove that the number of variables is strictly larger than a squared over 2k. So let's call it claim, the claim. The claim. The number of solutions to the equation, to the inequality. I plus j times k less than a is larger, strictly larger than a squared over 2k. Of course, we assume here that I and j are natural numbers, including zeros. And this is obvious if we write the following picture. So represent here, say, j, let this axis represent j, and this one represents I. Then our solutions are integer points lying under the following line. So this is our line. So this is A, and this is A over K. So, and we are interested in solutions lying strictly below the diagonal. And A squared over 2k is the area of that triangle forming by axis, and that line. Yes, of triangle. So we need to show that the number of integer points lying strictly below the diagonal is larger than its area. And this can be shown as follows. For each solution, draw a square whose left corner is that solution. Let's erase it. Write such a square. 1, 2, 3. Then each such square has some certain has an inner point with the triangle. So the number of the solution is equal to the total area of all those squares. And the point is that those squares must cover the entire triangle. Moreover, this cover is not precise, so it covers a little bit more. That requires, that implies that the number of solutions is strictly larger than the square, which equals to a squared over 2k. So indeed, the number of solutions is strictly larger than a squared of 2. And recalling that we know that by definition that a squared, by assumption that a squared over 2 is larger than n times n, is at least that much. So this is the number of equations. So this is the area. And we know that the number of monomials is strictly larger than the square, and the number of monomials is equal to the number of variables in our system. So we obtain that we indeed know that our constraints form a system of homogeneous linear equations where the number of variables is strictly larger than the number of equations, and so it has non-trivial solutions. So there is a non-trivial polynomial that is which can be found in step 1. And we just find any such polynomial using a Gauss elimination algorithm. Так, что-то я за это самое заговорился. Надо перерыв все-таки сделать. Давайте перерыв на 5 минут до 14:00. До 14:13. Ну, может быть, вопросы есть до перерыва еще. Вот по поводу этой леммы существования эры, как его найти. Так, нет вопросов? Ну, ладно.
Нет.
Ага, тогда перерыв до 14:13. Okay, let's resume the lecture. Recall our second step. On our second step, we need to show that when we substitute p of x for y in our polynomial, then we obtain 0. And here we assume that p coincides with initial f in many points. So to prove this, we need the following lemma, the second lemma. If the number of positions where f of x and f and p coincide is larger than or equal to a over n, then p r of x, p of x is a 0 as a polynomial. And this is proven as follows. So we know that there are certain, say, x1, x a over n points such that f of xi and p of xi coincide. That means that xi, p of xi is among the roots of R. So because the roots of R, without loss of generality, we can assume that all those points are the first a over n points. And this equality means that this is a root. Hence, this is the root of R over xy. And we know that once is the root of y, all those points are actually the roots of multiplicity at least n by construction. Multiplicity at least n. And this implies that xi already without the second component is a root of R of x, p of x of multiplicity n, at least n. Indeed, if we consider the polynomial R of xi plus certain z, p of xi plus z, we need to show that it has no monomials of degree less than n. But this may be expressed as R of xi plus z. This is a polynomial of z. P of xi plus z times certain q, polynomial q of z. And we know that if we consider certain variable z and say u here, this polynomial has no monomials of degree less than n. So that means that when we substitute z and zq of z, if we substitute z times q of z for the second variables, we will obtain no polynomials, no monomials of degree less than n. So that polynomial has no monomials of degree less than n. And this means that this is a root of these univariate polynomials of multiplicity at least n. Now we have a over n such x's. So in total, that polynomial R of x p of x has at least a over n times n roots, has more, even more than that. Sorry, at least, not more. Roots counting multiplicities. However, this is A, and we know that the k degree of R is less than A. When we substitute for a polynomial P, which has degree k for y, we obtain a polynomial of degree less than A, because the normal degree of R x p of x is equal to, actually is at most k degree of R of x, y. And this is because the degree of P is at most k. And we know that this is less than A. So the normal degree of that polynomial is less than the number of roots, which implies that actually that our conclusion that R of x p of x is 0. So the second lemma is proven. And now it remains to find the parameters which makes all the assumptions true. So we need that in the beginning, what do we know? So we need, let's see what have we used. We have that inequality that n times so choice of parameters. So we need to choose the parameters so that n times n plus 1 times n be strictly less than a squared over k. So let's choose, say n equal to n. And so we can choose a, b, about n approximately. This is n cubed, so n square root of n k. Right, and now you see that the second lemma states that if the number of coincidences is at least a over n, so if C of P f is at least a over n, which means approximately the square root of nk, then we obtain our conclusion then. So the number of coincidences is that I said, it's about square root of nk as desired. More specifically, here we need to take the ceiling, so we obtain a little bit worse than that. Then R of x p of x is 0. And that implies actually that R is divisible by y minus p of x. And why is this? Let's just divide R as a polynomial of y using a long division algorithm by a polynomial y minus p of x. We will obtain certain quotient q of y x and certain remainder s of x. The remainder is the polynomial of degree less than 1 in y, so this is just the polynomial of x. And just plug here y equal to p of x, everything. So we will obtain a zero polynomial on the left-hand side. We will obtain 0 here because this vanishes, plus s of x. So which implies that s is 0. So indeed, this implies that r is divisible by y minus p of x. And the algorithm now is the following. First of all, we find, so the algorithm is, as I said in the very beginning. On the first step, we find r of degree that much, which is approximately as we know that it is n square root of n k, such that all those guys are roots of multiplicity capital N, which is equal actually to the little n. Then we prove that all the initial polynomial, and actually all the polynomials whose tables are close to f, are roots of that polynomial, which implies that they are factors y minus p of x, or such polynomials are factors of r. And on the third step, we just factor r in irreducible polynomials. And this can be done in polynomial time using some smart algorithm, and we won't go into the details of that. And so we will represent R as certain S1, S2, S, say, L. And among all those factors, just single out all the factors of the form y minus p of x. It is well known that the representation of R as a product of reducible factors are unique up to multiplying by constants. And all those polynomials which are linear in y and which are factors are certainly reducible factors. And so among them, we just single out all polynomials of this type and form the list. So what will be the size of the list? The degree of R in Y is certainly at most, the degree in Y is at most A over K. When we divide, so the size of the list is about N times square root of N over K, which is certainly less than N square root of N. So as promised, the size of the list is at most N square root of N. Вот, все. Алгоритм описан, теорема доказана. Значит, есть вопросы? Сейчас тогда тест. Так. Так. Так, вот я кинул ссылку, значит, 27 минут 37 заканчиваю тест. 14:37.